In these set of notes, we're looking at objects that were rolling, that were not sliding or slipping. So they're maintaining contact as they were moving along a surface, whether that was rolling down something like a ramp or if it was just rolling along a surface. The difference being that if we have something that is in linear motion and sliding, we can say that there's friction or there's no friction, but all the molecules in the object are going to travel in that straight line together all at once. There's no relative motion between them. So we can treat the object as having its center of mass going through linear motion. And for that, we can set up dynamics equations, we can set up kinematics equations, or if it's something, for instance, like an object going down a ramp like this, we could set it up using conservation of energy. If, however, the object that we're talking about is circular and there's friction, that friction is going to apply a torque to the outside edge of the circular object if there's a force trying to push it forward. In the case of an object going downhill like this, the sine component of the weight would be trying to push it downhill. That would try to slide the entire object, but the force of friction would apply a torque, and that torque would create an angular acceleration, which would be linked together with the linear acceleration of the whole mass of the object. And just like we could for an object that was sliding, we can set up a net force equation, we could then set up some kinematics equations, but more importantly, if we want to try to use the conservation of energy, we need to set the conservation of energy equation up with a new term. We can have the gravitational potential energy that the object has because it's up above ground some height h, and we can have the kinetic energy that it'll have when it gets to the bottom of the ramp, but it's not just linear kinetic energy anymore. We'd have to have the linear or translational kinetic energy term, 1/2 mass times velocity squared, where that v is for the velocity of the center of mass. And then we'd also have to have a new term, that takes into account the fact that some of the molecules are undergoing circular motion, and while they're not moving forward all the time, they can be moving up to the right and down and going through that circular path. Molecules along the outside of the circle are going to be traveling a much different path than the molecules right at the center. And that equation we would use for rotational kinetic energy is 1/2 I for the rotational inertia times omega squared. So we're just replacing mass with rotational inertia and a linear velocity with an angular velocity. Using that, using those things, we can pretty much solve just about any equation we want. So let's take a look at this example of trying to figure out the total kinetic energy of an object that's rolling. Got a drink of my coffee here. If the object is in motion and it is not sliding, if there's a frictional force acting on the outside of the object, preventing it from sliding, it's undergoing circular motion while it's also going through translational motion. So we'd have the total kinetic energy would be translational plus rotational. And in this case, if it's a solid disk, we use rotational inertia of 1/2 mr squared. We'd also have to use the conversion factor that angular velocity is your linear velocity divided by radius. Once we make those substitutions into the equation that we defined up above, we can simplify this down and get an equation for the total kinetic energy. I apologize, I'm trying to erase stuff here and it's not erasing. We can get an expression for the total kinetic energy is 3/4 mv squared. And that'll allow us, if we knew how much, what sort of total energy there was, we could solve for the velocity. If instead this were the total kinetic energy expression after something had gone downhill, we could set it equal to the initial potential energy and solve. So let's try that right here. Let's do this example number 2. It says, suppose the disk in example 1 were released from rest at the top of a ramp such that its center was a height h above the ground. Using conservation of energy, develop an expression for how fast the disk would be moving at the bottom. So at the upper point, we'd have gravitational potential energy, no kinetic because it's not moving yet, and then when it gets down to the bottom, it'll have velocity, it'll have rotation as well, and we'd have the kinetic translational plus the kinetic rotational. And since this is the disk from example 1 that we just did above, we can substitute in place of the kinetics 3/4 mv squared, and in place of gravitational potential we can put m times g times h. Now if we wanted to solve this, so we just got to rearrange some things. We want to get it in terms of v, so the m's cancel out. It's always nice. We could move the 3/4 over to the other side. We'd have 4/3 gh equals v squared, or we can say that don't need the squared anymore. V is going to be equal to the square root of 4/3 gh. Now, if we were to have solved this using just translational motion, if we go back to what if there was no rolling? We would have mgh just equaling 1/2 mv squared, which if we solve would give us velocity is equal to the square root of 2gh. And if we look at the leading coefficient there inside of the radical, we're going to get a smaller coefficient than we had when it was just translational motion, meaning that the velocity of the object when it gets to the bottom of the ramp is going to be slower than if it were just sliding. Now, this is, of course, taking into account no rolling and no friction. Forgot to mention that. If there was friction, of course, then friction would be taking away some of the kinetic energy, possibly. But if something were sliding without friction, compared to rolling with friction, it's going to be slower when it rolls because some of the potential energy has to go into the rotational motion of the object instead of just the translational. Now, we could go ahead and put in numbers into this as well, but we don't really care about that. We just want to look at the process of how to get to the answer. Let's see what would it look like if instead of a solid disk, what if it was a hoop? If it was a hoop, then the rotational inertia is going to be different. We would have I for the hoop equals mr squared instead of 1/2 mr squared. And if we go through and we resolve what we did up here, we would just have to, well, I don't know, just redo it, I guess. Let's see. We've got the new kinetic energy, so we'll still have m times g times h for the potential. And that's going to turn into 1/2 mv squared for the translational motion, plus 1/2 the rotational inertia, mr squared, multiplied by v over r, the quantity squared. Switch colors there. This will become squared and squared. The r squareds will cancel, and I've got 1/2 mv squared again. And if I add that to 1/2 mv squared, I just get mv squared. So m times g times h would be equal to m times v squared. M's cancel, and then the v would be equal to square root of gh. And if we look at that, it's got a leading coefficient of 1. Instead of the 2 or the 4/3, it's got a leading coefficient of 1 in there, so this is slower still. Now, let's take a look at the setup of one more example problem here. This example is something that's kind of straight out of an AP question, where there's a toy car with 4 wheels. Each wheel has a mass, and each wheel has its own radius, and the car has a mass of that. And we want the body to be released from rest at the top of a ramp. What will the car's speed be at the bottom of the ramp? In this case, if we want to do this in terms of conservation of energy, because that's what's simplest, we would still have the car times g times h, turning into kinetic energy. And the kinetic energy here, though, is where we get tricky. What is in linear motion? Well, everything, the whole thing. And for this, we need to make sure we define here that the m of the car would be the mass of the body of the car plus 4 times the mass of the wheels. The car as a whole is made up of the body and 4 wheels. So when I say m car here, that's not the 0.5. That's 0.5 plus 4 of these little 0.1s. But the translational kinetic energy should be 1/2 mass of the car. Everything's moving, and it's all traveling down the ramp at some velocity v. But the rotational is going to be 1/2 times the rotational inertia of the 4 wheels. So we're going to have to say it's 4 times I of the wheel multiplied by omega squared. Now, if we set that up, we should be able to get to a solution. And it's going to take a little bit of time, but I want you to give that a shot.